So for conductive heat transfer as applied in a spherical geometric shape, so you have here R1 representing the inner radius of your sphere. So meaning we have the hollow sphere in this case, and R2 is the outer radius. You have T sub 1 as the temperature of the inmost part of your inner shell, that is right on the boundary of whatever is the fluid is inside the shell and this particular inner side. So that would be T sub 1. The outer temperature is T sub 2. If you're going to measure any particular distance from the center of the sphere, that would be represented by R in this case. So if we intend to determine the rate of heat transfer for this hollow sphere, and most of the time this hollow sphere has a fluid inside it, so that would be given by this particular formula. So you have the product of the conductive or the thermal conductivity of the material in which your sphere is made of. Then you have the difference of the two temperatures, the inner and the outer temperatures, and the difference of the reciprocals of the two radius, the inner and the outer radius of your sphere. Okay, so the direction of heat transfer in this case would be from the center of the hollow region outwards, so going out. But still, it's going to be measured, the distance that is to be measured on the center of these two concentric circles formed from the surfaces of your hollow sphere. So from the center of that. Now, if we will simplify this one, the formula that we have here, it could be written in this form. So you still have the temperature difference here, which is the driving force for heat transfer. And this one could be compared to the resistance expression for the other topics that we have discussed already concerning the different geometries in which we're going to apply conductive heat transfer. So I have here a sample problem concerning a hollow sphere and a hollow cylinder. So all in one problem, in sample problem number 1. And in this problem, it's the concept of convective heat transfer was already, I think, considered. Let me check. So it's not in this problem because we don't have it in here that we have a fluid, but we only have the mention of a hollow cylinder and a hollow sphere. So that would be, I think, in the second sample problem. So let me read the problem first to you. So the following data pertains to a hollow cylinder and hollow sphere made of the same material and having the same temperature drop over the wall thickness. So whatever is the wall thickness of your cylinder, or whatever is the wall thickness of your hollow sphere, you have the same temperature drop for that, and the two is made of the same material. So you're given this information that the inner radius of your sphere and of your cylinder is 0.1 meter, and the outside surface area of both is 1 square meter. Now, on the condition that the outer radius for both the geometries is the same, given that they have the same inner radius and they have the same outside surface area, you are to calculate the ratio of heat transfer or heat flow in the cylinder to that in the sphere. So being having to deal with these two, or having to use only these two information here, the inside radius and the outside surface area. So if you're going to actually solve this problem from the unknown going to what is to be required, when you are asked to determine the ratio of heat flow in the cylinder to that in the sphere, or that's the rate of heat transfer in the cylinder to that in the sphere, you're actually going to write this one. So that's always my suggestion to my student. You start with the unknown, of course, after you have written all the given information. In our case, class, you only have two information to work with. So you already have it in here, and then you are required for the ratio of the heat transfer rates. So if you're going to work your way up from the unknown going to the known, you work on the known data, then you will write the formula to determine the unknown. And the formula for the ratio of rate of heat transfer to the cylinder to that of the sphere would be this particular formula. For the cylinder, you'll be needing the length of the cylinder, you'll be needing the outer radius of that particular cylinder, and correspondingly the temperature drop, okay, or the difference in temperature of the inner and the outer surfaces. As for the sphere, you will be needing also the thermal conductivity constant. You will be needing the inner radius and the outer radius. So in the case of the cylinder, aside from the K and the two radius, just like in the sphere, you will be needing additional information, which is the length of that particular cylinder. So since we are already given in the problem that the inner radius is 0.1 and the outside surface area is 1 square meter, we can start with that of the sphere. That is determining the outer radius of the sphere, knowing that the outer radius rather of your cylinder will be the same to that. Now, question, why will you have to start working your way on the surface area of the sphere? You will have to start working your way on the surface area provided for the sphere. It's because for the sphere, you're only needing the radius so that you will get the surface area. You won't be needing the length. In the case of the cylinder, you will be needing both. So you have to use first the formula for the surface area of the sphere. So for the surface area of the sphere, we know it to be 4 pi r squared. And the r that you're going to use is the outer radius of that particular sphere because we're talking about the surface area. So using this particular formula and substituting the known value, one of the known values, which is the surface area of the sphere, the outside surface area that is, you'll be able to find the outer radius of the sphere, which is 0.282 meters. This outer radius of the sphere will be equal also to the outer radius of the cylinder. So working on that, since you already know the outer radius of your sphere, you substitute it on the formula this time for the surface area of your cylinder, which will now have the length, which we need in order that we can substitute everything here on the formula that we have below. So as for the area, the surface area of the sphere, you have 2 pi rn. We will substitute this same radius, r sub 2 radius to the sphere, to this cylinder because they're the same with that of the sphere. That would give us a length of the cylinder, which is 0.565 meters. So you now have everything that you need. That way you can get the ratio of the rates of heat transfer of the cylinder and the sphere, and the rest would be substitution to the formula which you have written in the first place. So when you solve a particular problem, I think I have suggested that to you already. You write the given, you write the required, and you write the formula or equation that will lead you to the required information. The formula in itself will help you, find your way through the unknowns or the variables that you need to determine first before you can complete the said formula so that you will know the unknown information. So in this case, we have already the value that we are trying to find, which is that ratio of heat transfer in the cylinder and in the sphere, and that is 1.756. Okay, so any questions so far with sample problem number 1 before I go to sample problem number 2? Meaning it's clear, we go to the Drexel, you're raising your hand.
Miss, may ara na siya like, miss, breakdown sang, miss, different elements niya, miss, like, for resistivity, nga, for the sphere, miss, nga, equation, kay ang gihatag, miss, do ka Q lang, gid, miss.
Again, you want the breakdown of the resistances for the sphere?
Yes, Miss Doka, ang different formulas, Miss, like for the resistance and for the actually resistance lang gid actually.
Okay, ng Drexel, the principle of heat transfer, whether you have a flat slab or you have a cylinder or you have a sphere, it's the same. So the amount of heat transfer on one particular resistance would be the same as the amount of heat transfer on another resistance. As long as these particular resistances are in series, in particular when we speak of the cylinder and of the sphere. In the case of the specific problem that we are discussing here, that was mentioned here, they have the same material and there was no mention about your sphere having composite or made of composite materials in layers. So meaning your sphere here and your cylinder is just made of one particular material and it's the same for both. So if your problem is, let's say for example, you have a sphere in which you have series of resistances, the formula in finding the heat transfer would be the same. You are to apply the same principle as if you're given a slab. The only difference here is that your area will be different than that of the slab. Because of the slab, you have a case of the length and the width of the slab. In the case of your sphere, you have the circumference times the length of that particular material, part of several materials in your sphere. Did I answer your question?
Yes, Miss. Pero like if sa cylinder, Miss, may log mean area, Miss. Sa sphere, Miss, may man siya different formula for area, Miss.
For area of the sphere, this is already, Iho, you mean you're going to determine the specific areas here for the sphere in which you have a composite, which is made of composite material, several materials in layers. Is that what you're asking?
Yes, Miss. Kay in the cylinder, Miss Doka, we had a breakdown of the different formulas, Miss. Like for the log mean
Mm-mm.
area, may formula,
Mm-mm.
and then for resistivity, may man formula. So Doka man, Miss. Kay ang gihatag di, Miss, Q lang gid, Miss Doka, straightforward.
Diretso na siya. So you want it like it would be shown to you in terms of the actual area in which your heat is going to pass through.
Yes, Miss.
Okay, let me check on the PowerPoint. I'll go back to the PowerPoint. Okay, so if I will share with you, I'll stop sharing here or I'll share a new one. Wait, class. Do you see my PowerPoint presentation? Do you see the slide?
Yes, Miss.
Okay, in the case of sphere, this is my problem because it will not show. So I'll just show to you na not naka-show siya. Amo lang eh. Okay, class. So you could see here the formula for the sphere. If you're asking Drexel for the breakdown of the areas for a sphere, wherein, let's say, for example, heat is going to be transferred from the annular region. If you open our book by John Kuplis for heat transfer, conductive heat transfer on sphere, wala siya naka-breakdown into lugmin areas. Straightforward nga ginbutang ang aton nga formula for heat transfer for a particular sphere like this with an annular region in here. So wala ko sang may mahatag nga in terms of area. Although if you give me a second, let me check on the soft copy of John Kuplis if there is. Let me just check. I'll just get my book, excuse me. Do you have a copy, a PDF copy of this book, Principles of Transport Processes by Jan Kuplis? If you have a copy of this, if not a hard copy, just a soft copy of this, and even McCabe, I haven't come across really a specific formula that breaks down, just like in the cylinder, the area concerning the sphere, if we're going to take into account conductive heat transfer. What you have in John Kuplis is just the integral that brings about this one, but there is no specific like singled out formula for the area in which we're going to determine the rate of heat transfer. Did I discuss heat transfer in differential equations, in which we have also a cylinder? Did you recall me discussing the one of the application of heat transfer in differential equation concerning a cylinder? Anyone? Did I discuss it in DE? If you recall, the process of determining the rate of heat transfer uses integral calculus, or starts with a differential equation and finishes it up with integration. Now, if you have a soft copy of John Kuplis, this particular formula that you are seeing came from a particular integral, which I did not write in here anymore. So one particular integral, which when integrated will yield already this particular expression. If I may suggest, you check it on your free time what that particular integral is. But Rexel, if you're really asking me for a specific formula for the area only, there's none. I can't give you one because I'm also using the book that is prescribed by PRC to use in this case, conductive heat transfer for a sphere or for the sphere. So if you use also McCabe, which is another book to use, a reference book to use, I think it's not also giving a breakdown of the area only, the area concerned for the sphere. But in principle, just like what I said a while ago, if you have a composite material in which your hollow sphere is made of, the rate of heat transfer to these particular materials are the same. Just like if you have a slab, we're working on a slab. So in this case, we have to use this particular formula wherein the radius are already in there together with the temperature difference. Okay, so let me go back to the one in Canvas. If you can find one particular reference that breaks down the area for a hollow sphere concerning conductive heat transfer, then you may share it also with me or with the entire class. But with our books, we don't have one for that, but we have for the cylinder. For the sphere, we don't. Okay, now this is for the sphere, and this is our first sample problem. So I'll go to the second one. The reason actually that I'm using this one, I think I got this particular sample problems in a PDF copy also of a resource from the internet. It's because our own books does not give us specific examples on this. The book simply gives you the principle behind and the formula with no example. So that is why I need to find other sources for this one. If you go to the chapter end problems of John Kuplis and that of, I can just state John Kuplis for now, it goes directly to letting you derive yourselves. You derive yourselves the formula that he gave. So that is the only problem that you can find in John Kuplis concerning application of conductive heat transfer to a hollow sphere. Let me read the chat. Okay. Thank you also, John, for bringing that up. Nobody asked me that before, probably because they saw already that in our reference books, there's none also. But nonetheless, who knows, maybe with the current scheme now in which we have the internet, you may be able to find a resource for that. Now, in here, for sample problem number 2, this time you are given only a hollow sphere. So you're given already the inner radius and the outer radius. and it is electrically heated at the inner surface at a rate of 10 raised to wait, glass. I need to change my glasses already. Can't see. Raised to 6 watt. Is this 6? 6 watt per meter squared. You just check, class, whether it's 6 or 5 watt per meter squared at the outer surface. At the outer surface, it dissipates heat by convection into a fluid at wait, cannot, this is too big also, I cannot read anymore. Into a fluid at 100 degrees Celsius and a heat transfer coefficient of 400 watt per meter squared Kelvin. Class, you may wonder why I'm talking, or this problem was already talking about heat transfer coefficient, which is still under the topic of convective heat transfer. I did only use this problem even if we've not yet discussed heat transfer via convection. It's because I need the formula. I need to illustrate the use of the formula to you. As to convective heat transfer, the formula will also be introduced here, but as to in principle, I will not discuss it anymore. It will have to wait when we are there already in convective heat transfer. Because in real cases, class, in the industry, it's a combination actually of convective and conductive heat transfer, especially in the transfer of fluids, whether we're talking of liquids or gases. So in this case, you see that both resistances, conductive and convective resistances, are considered in determining the total amount of heat that is being transferred. So going back to our problem, determine the temperature at the inside and on the outside surfaces of the sphere, talking about the hollow sphere. It may be presumed that there is no energy generation, so the electrically heated inmost part of your or inner surface of your hollow sphere does not generate any energy in the form of heat, or no energy is being generated in the hollow region. Now, and then the thermal conductivity of the material is constant. So even if the problem, class, is not mentioning that the thermal conductivity of the material is constant, we are to assume that it is constant. Though we know that this one is dependent on temperature, but we assume when we solve conductive heat transfer that the conductivity of the material is constant on the range of temperature that is given. So in this case, it was really specified by the problem that K is constant. So good. But even if it's not stated that it is constant, it's all right to assume that it is constant. So this is our thermal conductivity constant for the material. So our given for this problem would be the inner radius converted already to meters and the outer radius as well converted to meters in here. The rate of heat dissipation, meaning the rate in which heat is being transferred from the heated inmost surface of your sphere to the outermost surface of your sphere, is given as the rate in which heat is being transferred, which is 10 raised to 6 in here. This is the rate. By the way, actually, this is heat flux. Notice it's heat flux when you look at it, because the watt is the rate of heat transfer and the meter squared is measured per square area, meter square area. So for us to get the actual rate of heat transfer, we need to multiply this heat flux that is given by the surface area of our hollow sphere. In that case, we need to multiply it with the surface area of our sphere. So that would be 4 pi r sub 1 squared. Now, we did use the inner radius of our sphere because that is where that's where heating is starting from. So it's electrically heated at the inner surface at this particular rate. So if this is the rate of heat transfer from the inner surface, hasta pagwa class kung pila man na siya ka layer of thickness ang material ang imo nga sphere, amo man na siya gyapon ang rate of heat transfer. Basta wala lang losses. So in this case, we use this one. So we use the given heat flux and multiply it with the surface area using the inner radius of your sphere. And that would give you this particular amount of heat that is being transferred from the annular space, from uh, the hollow region of your sphere to the outermost part region of your sphere. If you're going to write in a simple graphical representation without having to draw the circular cross-section of your sphere, this is how it's going to look like. You have the inmost temperature of your sphere. You have the resistance R sub 1 of your uh, material in which your sphere is made of. And then you have the T sub 2 here, which is the boundary temperature of the outermost material in which your sphere is made of. And this one class is the resistance of the film. When we go to convective heat transfer, there's going to be a film resistance that will be offered in between a surface and a fluid outside that particular surface, or of the fluid that is flowing adjacent to that particular surface. Actually, this is still under the topic of convective heat transfer, but since it's already mentioned here, so this R12 is actually the resistance offered by the film of fluid right adjacent to the shell of your sphere, or right adjacent to the surface of your sphere. So if this is your sphere, actually class, there is some coating, some film that offers resistance to heat transfer also. And that particular resistance is convective heat transfer resistance. And it will have its own formula later when we go to convective heat transfer. In here, we will just simply account for it, assuming that you know already convective heat transfer. So again, I will emphasize this first resistance, T sub 1 is conductive resistance. T sub 2 is convective resistance due to the film of fluid on the outer surface of your sphere. T1, inner temperature of your sphere. T2, outer temperature of your sphere, or the boundary between the surface of your sphere, outer surface, and the film, offering resistance to flow. While TO here, as mentioned, is the temperature of the fluid. So take note, if you're used to assume that whatever is the temperature of the fluid on a particular surface, that would be the temperature on the surface itself. That is wrong, because in here, we have already what we call the T sub 2, which is the boundary temperature between the surface of the fluid and the film that is offering resistance to flow. So hindi masiling kita nga ang T sub 2 ta, ang outer temperature sang shell naton, or sang sphere naton is 100 man. Hindi na siya. So we need to determine this. So the problem is asking us to determine the temperature at the inside and the outside surfaces of the sphere. Meaning, we are actually looking, let me annotate, we are looking for these two. These two we're looking for, because this one is the temperature of the fluid in which your sphere is immersed into. Okay, now if we will account for the heat dissipated, as in principle, that would be the same here. If you're to account it here, that would be the same in here, and it would be the same from here to here, because that's a conductive heat transfer as in principle as we have discussed. So if we will determine the amount of heat transferred from here, the starting point, until the fluid outside the sphere or right on the surface of the sphere, so this would be our rate of heat transfer. And notice that now we account for two resistances. So the resistances that we are accounting is the conductive heat transfer. So conductive heat transfer resistance is already discussed to you, and that will take into account the inner and the outer radius of the sphere. Just a few minutes ago, I gave you the formula, and this is the resistance to that. So you have 4 pi k r sub 1 r sub 2. So we have already the conductive resistance. As for the convective resistance of the film of fluid on the outer surface of the sphere, that would be given by this formula. 1 over pi r sub 2 squared times the heat transfer coefficient that is given in the problem. So this is given actually in the problem, the heat transfer coefficient. So we multiply it here, everything in the denominator to give us this one. So we need to sum up the two resistances and the amount of heat dissipated here, which actually we based on the inner most part of your shell, because this one is the inner radius and this is the heat dissipated electrically in the hollow region of your sphere. And this value, take note, we equated here for the big Q. Because in principle, again, I will repeat for the nth time, the same lang na halin di pa kadto di, o kung halin lang diri pa kadto diri or diri pa kadto diri ang heat transfer rate. Okay, so we have used the 1130.4 watt, and then we equated it in here in our formula. This is our formula to get the T sub 1. That's the temperature here in the inner part of your sphere, the T sub 1. Now, the temperature of the inner surface then, based on what we have in here, is 270 degrees Celsius. Ini siya gin-simplify lang ang ininga line sang equation sa babaw to give you 270 degrees Celsius. So, under steady state conditions, heat flow through each section is the same. So this is the nth to the nth time reiteration. So what happened? The same amount, 1130.4, is equated this time to just this region here, the amount of heat transferred to this section, not region, to this section, which considers convective heat transfer, the resistance to convective heat transfer. So notice that you have now outer temperature, here T sub O, and this is your T sub 2. So it's T sub 2 minus T sub O because we assume that the temperature here is higher compared to this one because your direction of heat transfer is always from high temperature to low temperature. So we did T sub 2 minus T sub O because anyway, you are equating here the magnitude of the heat that is transferred. If you interchange the manner of subtraction, you might as well place here negative in here. That will make it true just the same. Okay, so this is just the magnitude of heat that was transferred. So in this case now, with R sub 2 accounted for, or R sub T2, the resistance to convective heat transfer used here, and you have this temperature in here, temperature difference in here, you'll be able to get the T sub 2. So in the process, you get T sub 1 and T sub 2, the inner and the outer temperatures of your sphere. Now, before I go to the last topic, do you have any question here? Hindi lang taanay mag-question sa convective heat transfer because the formula will be again introduced to you after this topic. That would be in module 3. But in here, it's already considered together with conduction. So it could be class that in a problem, the problem itself will not specify that, hey, you are to solve for both, ha? No, you are the one who's going to think of it. What's going to be the resistances that I'm going to consider? Will it be pure conductive heat transfer, or I need to consider in this time convective heat transfer? The problem itself will also give you a Q, because it will give you the heat transfer coefficient. If it will not give you the heat transfer coefficient, there's a table in your Paris handbook, chemical engineer's handbook, that gives you the heat transfer coefficients of fluids. And that would be the H that you will use in this formula here. But we'll go there when we're done with this topic. So any question in here? So you work out with two informations, actually three only, this, and the temperature of the fluid on the surface, outer surface of the sphere. There are no more questions here. I'll go to conduction through materials in parallel. What you have in here, class, is just the formula. So I will share to you the slide where this particular topic is mentioned or discussed. Okay, so we go to Fourier's law applied through materials in parallel. I'll first start here so that you will understand why there's a need for you to add in this case. There are instances wherein you're given composite resistances. Let's say this is the direction of heat transfer. You need not worry about the A and the C here because they are all the areas of these surfaces are all perpendicular to the direction of heat flow, and they are said to be in series. A and C are in series. Actually, A, B, C are in series, or shall I say A, B, A, D, C are also in series. But the other challenge here is that your middlemost composite material is made of two resistances in parallel. So if this had been only A, B, C without the D, so we won't have another topic to discuss here because it's just a series of resistances. But since your middlemost, material here is made of two different materials in itself, this is a case of what we call parallel resistances. So in parallel resistances, the amount of Q that you will be accounting here will be the sum of the Q in here and in here. Unlike if, let's say, for example, I take these two out of the picture, the amount of heat transfer in A should be equal to the amount of heat transferred in C. Or shall I say the amount of heat transferred passing through A and C combined will just the same as the amount of heat transferred that passed through A and C standing alone or considered alone. Now, in this case, class, the amount of heat transfer in A here, which is equal to the amount of heat transfer in C, should be equal to the amount of heat that is to be transferred to B and D. So this time you need to add the Q in B and D. So if I will show now, go back to the slide, which has the formula. The formula that you are seeing here that accounts for the total amount of heat transfer. In my illustration class here, that would be applied to B and D. So meaning this should be Q sub B and Q sub D. You add these two, you add the Q sub B and the Q sub D, the total amount of transferred heat here is equal to the amount of heat transferred in A equal to the amount of heat transferred on C. That would be the same amount of heat that is transferred to this entire composite resistance. So your book actually, again, does not give any example on parallel resistances. It simply gives you the formula to use in which you are this time not equating amounts of heat transferred, but you are adding because your resistances are in parallel. If you also need a copy of the book, the soft copy, I can share it with you, both that of John Couplis and McCabe, so you can check yourselves. There aren't even no problems being discussed on this. Probably the author already assumes that the reader would know how to use the formula, and that would be for this particular scenario. Now, in parallel resistances class, it's noted that since, let's say, for example, I go back to my illustration here. Let's say I'll place here T1, T2, T3, T4. Since these two materials are in parallel, your T1 is equal to T3 and your T2 is equal to T4. But nonetheless, when we speak of difference in temperatures, this is how they are labeled when you write them in the form of a formula. So in the formula that you are seeing here, it's really written as T1 minus T2 and T3 minus T4, but T1 and T3 are equal, and T2 and T4 are equal if these two materials are in parallel. And I have defined here also what does T1, T2, T3, and T4 represents. So these are your four temperatures, but the two pairs are actually equal to each other. That yes, you have two pairs of equal temperatures. Okay. Now, I suggest if you want to start on the fundamentals, you would like to solve problems using the fundamentals, you use the book by John Kuplis, which I'll be sharing to you in a little while, at the chapter end on conductive heat transfer. Then, when you think you're comfortable already and you have already grasped how you're going to apply the principles and the formula, then you go to McCabe, because McCabe's presentation is quite different than that of John Kuplis. But what is good about John Kuplis is some problems, or there are a lot of problems which have answers. In the case of McCabe, if you don't have the soft copy of the solutions manual, you won't know whether you're doing the right thing or not. Because even if you have the solutions manual, the way it's presented, the solution I'm referring to is actually very different. So what I do then when I was a student, I simply look at the answer, then work it the way I understood it. And at times, if you already grasp the principle correctly, miski ano pa na siyang imo, pag work through sa formula, nga naintindihan mo nga nagamuna, you will still be arriving at the same answer. Even if you're going to compare your solution, it's different than what you are seeing actually in solutions manual. So the way the solution there is maybe really quite different than the way you understood it yourselves. So what is important is you understand it and you are able to apply the principle and the formula. Okay, so this ends the topic on conductive heat transfer. Do you have any questions so far here? I will stop sharing. I have already shared the